so we are going to derive a finite difference form from a heat diffusion equation at steady state and no heat generation. So let's begin. So in the case, let's write this out real quick. So if we're going to use Cartesian coordinates, we're going to have the gradient here, x, temperature gradient, second derivative, plus, this is all at steady state. Alright, oh. Okay, so this is at steady state and we're using Cartesian coordinates, but we also said we don't have heat generation, so that's going to go to 0. So we can rewrite this. Change the temperature with respect to time. Alright, so there's a couple of things that we can do. There's like one thing we can do to simplify this down more. So if we divide by k on both sides, we rewrite this. So density, heat capacity, thermal diffusivity, change in temperature with respect to time, partial derivative. Alright, so this is actually equal to 1 over alpha. I'm going to simplify that down to make it easier for us to deal with. So, and then multiply it back over so we don't have a 1 over alpha, so we have alpha, second order, partial derivative, temperature over change time, with respect to time. Cool. So the next thing we're going to do to continue into a finite differencing form is, let's say we have a temperature at a specific time, we'll call that N, and a specific place, we'll call that J. So we can break this into pieces where we're going to have X equal to J, because that's our position, J, change, and X. We're going to do an approximation to the derivation eventually. And then we're going to have time, T, is going to be equal to N, change in time. So these here are just the J, the N. These are just integers. They're integer multiples of position and time. Write that down. Awesome. So now we can actually start to write this out, where we can break this apart. We can start to break this up where we take this and turn it into with a position. So we'll have time, write that out, applying what we have here. And we're going to set that equal to this. We're going to split this up a little bit. So we'll still have alpha here, but we're going to actually pull out a partial derivative with respect to x, so that now we have a partial derivative with respect to t with temperature with respect to x. So that's our temperature gradient. So now we can take this and look that we used the partial derivative with respect to t here on this top part. We're going to make an approximation to the derivative now. So what we're going to do is we're actually going to do two of these. One of these is going to be for j plus 1, and one of these is going to be for j minus 1. So a step forward as well as a step back. So we're having the position step. So we're setting both of these up. We're going to apply it to our setup with change in x. So, so these are approximations to the derivative that we are making right now. So we're taking that step forward, keeping it at the same time, because this is our change in time over here. We're going to subtract it. There's j, and that's an n. All over change in position. And then we're going to do the same, but we're going to have t to the j, minus t, and j minus 1, all over x. Alright, so now we can open this up a little bit more. We can have this equal to we're going to subtract these from each other all over the change in position. Over change in position. Write that all out. All over the change in position. Right there. So now we can simplify this. So we're going to continue. And now we can simplify it down to t j plus 1 n. So that's the step forward in the position. And we're actually minus 2t n plus, because these two minuses cancel. It's going to be this is all over x squared. Oh, and we still have alpha front. Alpha. Good. Okay. So now we can pull some things out. So we can do now all we have to do is simplify. So we're gonna have t j plus 1 and so we're looking for the temperature at the next position step. That's what we're solving for. And we're setting this equal to now we have a t j to the n, the one right before it, is equal to. So before we added this to this side, we pulled out this change in x squared. So we're going to have alpha over the change in x squared, and then we multiplied it by the change in time, change in t, and then we write out this t to the n for time j plus 1 is equal to 2 t j to the n plus t t j minus 1 to the n. Write this around. So now we have solved for a finite differencing form where we have this specifically. So this can be treated as a number, this part, and we can signify that even as r later, in which we will be using to perform calculations in order to see over a gradient of a bar. So earlier in this video, we have derived a finite differencing formula using the heat diffusion equation for Cartesian coordinates with no energy generated at constant state. So now we will be showing how to plot this temperature profile in the case that this is across a bar whose initial temp is at 300 degrees Kelvin, with the left side being at 350 degrees and the right side Kelvin, and the right side being at 400 Kelvin. So we have already begun over here with importing NumPy as NP. This is our overall, it's a very versatile library which we will be using to perform our calculations today. We have also imported Plotly. This will allow us to have a visual plot of the overall temperature profile, which we will see later. This last line is total personal preference. It will be, its only reasoning is just due to overall viewing and personal accessibility, especially since I also currently have collaboratory in dark mode currently, just for continuity reasons. So this last line is totally optional. So we are going to begin looking at our finite differencing formula, where we need to establish our amount of slices within the bar. So we are going to denote this as an x. We're going to set this equal to 100. So we're going to have 100 slices in the bar that we are going to analyze. We're also going to look at the number of time steps that we are going to use. And since we want to see a pretty full temperature profile, we're going to put this at 20,000 time steps to see it really over time. And as provided in the problem statement, we will be denoting r as 0.1. So you might remember r as being alpha multiplied by the change in time over the change in position squared, change in x squared. But we will be simplifying this and denoting this as r, and we will be analyzing it at r equals 0.1. Let's enter onto the next line. So now we will be defining the temperature across the bar. So temperature, T, is equal to NP full across the bar with, now you can see that we have the shape and the fill value. So to begin with, the shape, as we see up there, is NX, which we defined as 100 slices. And then the fill is our initial temperature of the bar, which is 300. You see I put a dot after that. That is because it will not be an integer. This can be a decimal value, so we are seeing that full gradient. Enter. We'll continue with our arrangement of the slices. So we will into an array. So we have x equals in the x direction. So this allows us to have x in the equation. P dot a range and x. So we're looking at, and x is a range of all of the slices. And now we are going to define our first slice. So this is T0 is equal to 350 Kelvin. Of course, we're putting a dot after that. And we're going to also define the temperature, provide the temperature of the last slice. That is T of -1. That is equal to 400 Kelvin. These are both provided in the problem statement. So I'm going to Shift enter that to establish those. And now we are going to continue on to making the plot. So now we are looking to make a figure, so fig equals, we're making a subplot with rows and columns. So since this is a one-dimensional, we are going to have one row and one column, so we'll type that out. And so we have rows, as it's guiding us through here, equals 1, and then columns, equals. Now we are also making a scatter plot here, so we have fig dot add scatter as we make these calculations. And continue with, we have x. For our x, we have x as we defined above here, which is the range of nx, and of course y, our dependent, is y equals t, so our temperature is the guidance for that. I'm gonna do mode equals lines, and we're gonna name it temp pro for temperature profile. Now we are going to continue with taking the finite differencing equation that we derived from the heat diffusion equation, and we are going to put that into this code so that we can apply it to the overall temperature profile of the bar we just made. So we're continuing on. So for I in range, we're going to have starting with 1 and then time step plus 1. Going to continue with putting in our finite differencing equation formula. So we're going from 1. So this is the space after the initial point, which is defined as 350. If we were able to show, if we were able to plot or just ask for t, it would give us a whole array from the initial and show us that it would be, the first would be 350 to 400, and everything in between would be 300. I can show that right now, actually. So, T. Oh, you can see that right here. So the first one is 350 as we defined. Second one is 400. And we have this entire array totaling 100 slices from 350 to 400. Yep. So now we will continue with this. -1 equals, and now we're just typing out the equation with respect to the x function of each. Oh, so this is from 1, -1. And you can refer earlier to the video to the finding this formula. We are now just putting it into terms for calculating. There's D2. That goes from 2 all the way through minus 2 times t from the first term to the last term plus t colon -2. So as you can see how we relate this equation here to the equation we derived. So this were the over here, this is our t to the n j plus 1, and this is overall t to the with the j. So the subscript is j for each of these. So this is j plus 1, this is just j, and this is minus 1, as you can tell. We're going from that beginning all the way to -2. So this would be like, this would like it numbers. So like in Python we start with 0, but this would be from 1 to 99, and this would be 0 to 98, and this would be 0 to 97, or is that 2 to 99? I believe. So, and these are our, we subtracted this initial point from here. Yep, so that looks good. And now we can do if I as a check. And this is a modulo. This is a very commonly used function. 0. And now that's the check. So now we can add fig dot add scatter. And of course, x equals x as we defined, y is equal to t, mode, of course, is equal to lines. And we're gonna keep name, since this is if I, and for I, we're gonna have the name equal to f I. Awesome. And now we're going to do fig dot show, and it should show us the temperature profile at at these current points. So when we have 100 slices, 20,000 time steps at r equals 0.1. Invalid syntax. Let's look this over. I guess we can, maybe it's my name. Let's just do, maybe since we're with the initial line 2, initial. Oh, name equals. Valid syntax 0. Oh, I believe we need this. And there we have it. So this is, we're showing 20,000 time steps just to see an overall. But here is our temperature profile with 20,000 time steps with 100 slices in the bar. You can see over time it becomes this gradual until it seems like this gradual swoop. And I believe if we continue to increase the time steps, this can become more and more of a straight line. Let's try that. Let's go 50,000. Shift enter, shift enter, shift enter. Yes, it does become more of a straight line. We are kind of overloading it right now. but we can see here that it does become more of a straight line. So another thing that we wanted to try is we were first told to use r equals 0.1, but we were also told to try r equals 0.55. So let's make that change. Shift enter, shift enter, shift enter. And now we see something rather interesting. So these are extremely large numbers we see here. It's 2 times 10 to the 234th, 4 times 10 to the negative 2. Yeah, so this is a very odd. We see some very sharp extremes and oscillations. So this is known as an instability, which will be explained to better understand why this occurs, especially as we use r equals 0.5 compared to r equals 0.1. We could even compare this to r equals 0.55.